So what does that mean? That means delta of x1, x2, xn is same as mod of xn to power b delta of x1 upon mod of xn, xn minus 1 upon mod of xn, and xn upon mod of xn. So my deltas would be mod of xn to power b and some function of x1 upon mod of xn, xn minus 1 upon mod of xn, and xn upon mod of xn. I want to make my life a little bit simpler. I want to convert this into as a function of, let us say, u of x1 upon xn, xn minus 1 upon xn, and xn upon mod xn. Can I write down this like this? This as a function of mod of xn to power p and some function of this. I'll be able to write down this as a function of this, provided this argument over here is a one-to-one function of x1 upon xn, xn minus 1 upon xn, and xn upon mod of xn. So that is very simple. Suppose this is known. If this is known, then I know xn upon mod of xn. Xn upon mod of xn is positive. Sorry, if xn is positive, it is 1. And it is minus 1, that means xn is negative. So that means if I know this, I know this is plus 1 or minus 1. If I know that this is plus 1 or minus 1, I know the sign of xn. If I know the sign of xn, this would be either x1 upon xn or x1 upon minus xn. So that would be a function of this quantity itself. And conversely, also you can use the same argument. If I know this, I know the sign of this. If I know the sign of this, then x1 upon xn and x1 upon mod of xn are one-to-one functions. So this implies that delta of x1, x2, xn is same as mod of xn to power b. Let me write down this in the division. So u of, let me call this as z1, z2, zn minus 1. So let me write down this as u star so that, or let me write down this as v. So this is some function of this quantity, and v I can write down as 1 upon u of this. Because finally I want my delta to be positive, so v should also be. So v should be positive, so u is positive. And what is my zi? Zi is nothing but xi upon xn for I is equal to 1 to n minus 1. And Zn is nothing but xn upon mod of xn. Now note that Zn can take only two values, minus 1 and 1, depending on whether xn is negative or xn is positive. Now note that if I consider just estimator mod of xn to power p as an estimator, mod of xn to power b, does this belongs to the class of invariant estimator or not? To see that whether it belongs to class of invariant estimator or not, what I do is I transformed original data into cx1, cx2, cxn, which I do over here, and I see then this gets converted into c to power b into mod of xn to power b. C is positive, so that is why mod of c to power b into mod of xn to power b would become c to power b mod of xn to power b. So that means this is invariant. So this is an invariant estimator. Mod of xn to power b itself is an invariant estimator. So what I have seen is delta is invariant if and only if delta can be written as mod of xn to power b upon some function of z1, z2, zn minus 1, and zn, where zi's are given by this. Now the question is, can I replace mod of xn to power b by any equivariant estimator? And the answer is yes. So that you can write down in terms of a lemma. Let delta naught be any equivariant estimator. That means delta naught of cx1, cx2, cxn is same as c to power b delta naught of x1, x2, xn. Then any another equivariant estimator can be written as delta of x1, x2, xn. So the only change happening over here is this mod of xn to power b can be replaced by delta naught of by u of z1, z2, zn minus 1. Zn for some function u from 0 infinity to n minus 1, because z1, z2, zn minus 1 for I is equal to 1 to n minus 1, they can take value 0 to rn minus 1 cross zn. Zn can take value only minus 1 to 1. So the last argument only takes value minus 1 to 1. And u has to be positive, so u 0 to infinity. Because delta naught is positive, and I want my delta to be positive because theta to power b is positive. Okay. So now we have done that. So now we would be in a now we have to examine whether I can find the best invariant estimator or not. Now to do that, first let us see whether G bar acts transitively on theta or not. For that, let theta 1 and theta 2 belongs to capital theta. So to show that G bar acts transitively on theta, what I have to show is theta 1 is related to theta 2 through some G bar C. And that is not difficult because theta 1 can be written as theta 1 by theta 2 into theta 2, which is nothing but G bar of theta 1 by theta 2, theta 2. So this is same as C. So that means theta 1 is G bar C of theta 2 for some C. This implies that theta 1 is same as G bar C of theta 2 for some C greater than 0. What does that mean? That means G bar acts transitively. Now we have seen that if G bar acts transitively, then we have a lot of advantage. Because now the risk of any invariant estimator no longer depends on theta. So this implies that for any delta belongs to di, r delta theta is same as r delta 1 which is nothing but expected value of theta is equal to 1 of L theta Wx, but my theta is 1, so L1 because risk at the point theta is equal to 1. But my loss function is nothing but W of A by theta to power B. So it is same as W of delta of x. So if I look at let delta naught belonging to di be fixed and let delta be any other estimator which is invariant, then it would be of the type this, and delta is any another invariant estimator. That means delta is of the type delta naught of x of u of z. Then what is r delta theta? So delta naught is fixed. So as you vary your function u, you get different invariant estimators. So that means the only varying quantity over here is u. As you vary u, you get different invariant estimator. So R delta theta is nothing but E theta of W of delta naught x, so that means same as W of delta naught x by U of z. So what I do? I make this conditional expectation as, this expectation does not depend on theta. So I convert this expectation into expectation of a conditional expectation. So this makes E theta is equal to 1, E theta is equal to 1, expectation of a conditional expectation. So W of given z. Now, as I've told you, the only varying quantity over here is u, because theta is fixed, theta is equal to 1. As you vary u, you get different quantities of this inner expectation. So what I try to do is I try to find a u for which this inner expectation is minimum. Note that it does not depend on theta. So I can think of finding a u for which minimizes this quantity. So let u star, which is u star of z, where z is nothing but be such that for every fixed z, u star which is u star z minimizes this inner expectation, which is, let me call this as psi of u, which is expected value of W of delta naught x divided by u, given that z is equal to small z. Actually, better way to write down this PD for, you can remove that. So what I do is, as I said, the goal is to minimize this for every fixed z. So if this inner expectation minimized for every fixed z, then the outer expectation is minimized for every z. Because if I am able to find a u star such that this is minimum, the corresponding u star would minimize this whole expectation, as we did in the location case. So the whole problem reduces to minimizing this quantity. Okay? So let us see further. Let us try to see if I can write down this in terms of a location kind of a scenario where I was dealing with loss function of the type W of A minus theta. This is E theta is equal to 1. So this can be written as let me just come over here, e to power theta is equal to 1. Now this quantity, note that this is positive. So I can write down this as e to power log of this quantity. So this becomes W of e to power log of delta naught upon u. So that means log of delta naught x minus log of u. All right, what does that becomes? this is becomes E at theta is equal to 1 of W star of and then given Z is equal to Z. W star of e power W star of log of delta naught x minus given Z is equal to Z. What I know is my W star is convex. In, let me denote this log u as u star or t or any other variable. Yeah, t. Log u as t. So this is convex in t. Right? Because W star is nothing but W of e to power t. So basically, if you look at, let us try to see this function. W star of log of delta naught x minus t is nothing but, so what I have assumed is my W star is convex, because W star is nothing but W of e to power t. I have assumed that W of e to power t is convex. If W of e to power t is convex, which is equivalent to that W star is convex, so what I am saying is W star is convex and non-monotone. That is what my assumption was to begin with, that W of e to power t is convex and non-monotone. This implies that this whole quantity is convex and non-monotone. In T. W star is convex and non. This implies that W star log of delta naught x minus T is convex and non-monotone in T. What does that mean? That means psi u is convex and non-monotone T, which is T is nothing but log u. So what I try to do is I can then find out what is the minimizing T, which is equivalent to finding the minimizing log of u. And log of u and u are one-to-one function. So once you have found out the minimizing log u, you know what is the minimizing u. So that is the whole idea. So the minimizing T exists, so minimizing log u exists, so minimizing u exists. So this implies that minimum risk invariant estimator exists, provided W of e to power t is convex and non-monotone. That just follows from this, because once I have assumed that my W of e to power t is convex and non-monotone, then that means where W star t is nothing but W of e to power t. So I'll be able to find a minimizing t for any fixed z. If I'm able to find minimizing t, which is equivalent to saying that I'm able to find the minimizing minimizing log of u. If you are able to find out a minimizing log of u, you can get the minimizing u, because log of u and u are one-to-one function. So I get the theorem, which is as follows. Let me write down the exact statement. So theorem says delta naught delta I is given. So this is any given invariant estimator. A for every z belonging to Rn minus 1 cross minus 1 to 1, suppose that u star, which is same as u star of z, minimizes psi of u, which is basically this quantity, E of theta is equal to 1. W of delta naught x given u, given z is equal to z. Then MRIE of theta to the power b is delta star x. Delta naught x was that fixed. The minimizing u you have already find, which is u star of z. Now we have seen that if my w of e to power t is convex and non-monotone, the minimizing function u star exists. So the function u star in A exists if RT, which is w of e to power t, is convex and non-monotone. It is unique if RT is strictly convex. It may exist in many other situations, but certainly if w of e to power t is convex and non-monotone, then the existence of MRIE is guaranteed. And MRI would be unique provided w of e to power t is strictly convex. Now, we saw in the location case that minimizing these conditional expectations involve finding the conditional expectation. So is there a way I can get rid of this conditional expectation? So in the location case, if you recall, we appealed to the Basu's theorem, which says if a statistics is complete and sufficient, so if T is complete and sufficient and V is ancillary, then T and V are independent. In the location case, we saw that corresponding in place of Z there I had a D. D turns out to be ancillary. So if the same thing happens over here, that Z turns out to be ancillary, then this suggests that I should choose my delta naught belonging to Di such that delta naught is a function of a complete sufficient statistic. Then delta naught and Z would become independent, and then life becomes simpler. Then I don't have to deal with this conditional expectation. So the question is whether this Z is ancillary or not. That is straightforward to see. So my Z was x1 upon xn, xn minus 1 upon xn, and xn upon mod of xn. Now note that what we have seen is if we apply the transformation Cx1, Cx2, Cxn, I again remain in the same family except that theta gets replaced by C theta. So that means if I apply the transformation as C as 1 by theta, so that means x1 by theta, x2 by theta, and xn by theta. So if I look at x1 by theta, xn by theta, I am in the same family except that my theta gets converted into theta is equal to 1. Has a distribution function f of theta is equal to 1, x1, x2, xn. So there is no theta. F is known to us. So that means x1 upon theta, x2 upon theta, and xn upon theta is ancillary. So let me call this as T1, T2, Tn. That means T1, T2, Tn is ancillary. Right? This is why, because we saw that if x1, x2, xn has a distribution function f theta, then Cx1, Cx2, Cxn has a distribution function f of C theta. What is happening in place of C? It is 1 by theta. So f of C theta would become f of C as 1 by theta into theta f of 1. Theta is equal to 1. So it no longer depends on theta. So T1, T2, Tn is ancillary. It would normally you use ancillary for statistic. This is not a statistic, but let me use it in generality so that when I say it is ancillary, that means its distribution does not depend on theta. So the distribution of the quantity T1, T2, Tn does not depend on theta. Let us try to see jet. Jet can be written as, I can divide both the side by theta, numerator, denominator, things don't change. So it becomes T1 upon Tn. Tn minus 1 upon Tn, and then this becomes Tn upon mod of Tn, because theta is positive. Z is this, and I know that joint distribution of T1, T2, Tn does not depend on theta. So joint distribution of any function of T1, T2, Tn will not depend on theta. So in particular, joint distribution of this whole quantity does not depend on theta, which says that joint distribution of Z1, Z2, Zn will not depend on theta. So this implies that Z is ancillary. So this suggests that I choose delta naught to be a function of complete sufficient statistic. So I choose delta naught belonging to Di such that delta naught is a function of complete then I know that this being a function of complete sufficient statistic, this being ancillary, the two are independent, so conditional expectation would be same as unconditional expectation. So that means now I have to minimize this. Now I have to minimize this, there is no Z now. So that means this U is going to be constant, it no longer depends on Z. So then MRI is, let me just erase this much, delta star x as delta naught x by U. U no longer now depends on Z, because this conditional expectation now no longer depends on Z. Where, so let me write down this as U star, where U star minimizes, now in this case it will be this conditional expectation. Psi of U, which is E theta is equal to 1, W of delta naught x by U, there is no conditional expectation. So if I can choose delta naught to be a function of complete sufficient statistic, then by virtue of Z being ancillary, my conditional expectation becomes unconditional expectation. Now note that you could have chosen x naught to delta naught to be mod of xn to power b, because that is invariant. Then I cannot apply this result, because then I have to deal with conditional expectations. So to avoid that, you try to choose delta naught such that delta naught is a function of a complete sufficient statistic. So let's try to see some loss functions which make sense over here. So my L theta A is nothing but W of A by theta to the power B. So one such loss function could be W of T is same as T minus 1 whole square. T belongs to R. This is certainly convex. So L theta A will turn out to be A by theta to the power B minus 1 whole square. One can consider Wt to be mod of T minus 1 also. In this case, L theta A will turn out to be mod of A theta to the power B minus 1. A in the xn space, theta in the parameter space. Now one can see that in this case, one is able to find this U star, depending on Z or not depending on Z, that depends on the fact whether you have chosen delta naught to be a function of complete sufficient statistic or not. So in this case, let us take psi t to be W of e to power t. What does W of e to power t means? Yeah? This is same as e to power t minus 1 whole square. What I have to see, it should be convex and non-monotone. So psi prime t turns out to be 2 times e to power t minus 1 into e to power t, which is nothing but 2 times e to power 2t minus e to power t. I can take the double derivative to determine the convexity. So psi double prime t is 2 times e to power 2t is nothing but twice of e to power t, e 2t minus e to power t. All right? 2 of e to power t minus 1. So let me again check whether W of e to power t is nothing but e to power t minus 1 whole square, psi prime t is nothing but 2 times e to power t minus 1 into e to power t, which is same as 2 times e to power 2t minus e to power t. Psi double prime t is same as 2 times 2 e to power 2t minus e to power t, which is same as twice e to power t into 2 e to power t minus 1, right? Which is always greater than or equal to 0 for every t positive. So it is convex. What about monotone? Let us try to see psi prime t. Non-monotone, psi prime t is greater than 0. It is increasing if and only if 2 times e to power 2t minus t is greater than 0. So that means e to power t is greater than 1. Sorry, I made a mistake because my here this W e to power t is defined on whole t to power r. If this is defined in whole e to power t to power r, can I say that this quantity is always greater than or equal to 0? Certainly not. because as t goes to minus infinity, this goes to 0 and you may get negative values. Yeah, so there is a problem. So here, this function is not convex. So as such, directly from that result, I cannot say that the MRI exists or not. But as we'll see that, if I try to do it using the first principle, I'm able to find the minimizing U star Z. So let us try to see what is that. And I'll just try to finish that over here. So as such, I do not know whether minimizing U star Z exists or not. So what I do is I consider expected value at theta is equal to 1 of W is nothing but delta naught x by U minus 1 whole square given Z is equal to Z. So what does that mean? That is becomes 1 upon U square, theta is equal to 1 of delta naught square minus 2 by U and plus 1. Let us take the derivative. That becomes minus 2 by U cube E theta is equal to 1 delta naught square x given Z is equal to Z plus 2 by U square Now note that when I'm trying to minimize this respect to U, my U has to be positive. Right? So what does that mean? So I try to see when, so if one way is you can take the double derivative, or you can see when this is greater than 0. You can see the increasing and decreasing behavior. So this is greater than 0, what does that mean? That means U is greater than E theta is equal to 1 That means U psi U is an increasing function for U greater than 1 and decreasing function for U less than 1. So your psi U behaves like this. And this is quantity U star. Right? That is where the minimum is, because after this it is increasing and it is decreasing before that. So my psi U says that beyond this point it is increasing, before this it is decreasing, because decreasing you can see when it is less than 0. So what does that mean? I've got, in this case, my minimizing U star, although this does not satisfy that W of e to power t is convex and non-monotone. So U star Z in this case turns out to be E theta is equal to 1 delta naught square x given Z and your MRI is Good. So suddenly, if delta naught is a function of a complete sufficient statistic, this conditional expectation becomes unconditional expectation. So this U star will not depend on Z. So let me stop over here. So this was basically, I wanted to review the scale invariant part so that you become very comfortable with this whole notion, because this invariance itself is slightly complicated in the sense it is different from the things which you did in earlier courses. And that's the reason why I repeated this whole scale invariant estimation so that you can get a better feel of the invariance. What I'm going to do next time is, in the case of squared error loss function, I'll give you explicit expression of the minimum risk invariant estimation, as we did in the case of location invariant estimation. So let me stop over here. That will do next time. Thank you very much.